Good morning, students. Welcome back to chemistry class. And last class we completed. We have marked the book back questions up to unit number 3 up to question number 36. We completed. Today remaining questions we are going to mark. Okay, the students, if you having time, any time you have, you should study. Okay, but I'm giving only 2 questions or 3 questions to study. But you don't not only that question you should study, you should other questions, remaining questions you try to study, and book in question you should read the book. Okay, you should read the book and take the 1 mark questions. Okay, it's very important for the midterm examination, 3rd unit and 4th unit having. Okay, students, all of you take page number 97 now. Page number 97. Question number 37. Why halogens act as oxidizing agent? Why halogens act as oxidizing agent? Okay, here question number 37. It is not in book, so I have written the note. Why halogens act as the oxidizing agent? Answer: halogen act as oxidizing agent. Their electronic configuration is NH2 and NP5. You know, halogens are fluorine, chlorine, bromine, iodine. These are all are halogens. So each halogens have the electronic configuration NH2 and NP5. NH2 and NP5. Okay, NH2 NP5 configuration. So NH2 NP5 means this is the outermost electronic configuration. So all the halogens are readily to gain 1 electron to attain the nearest noble gas configuration. So all the halogens are readily to gain. Okay, to get the now to NH2 NP5 means totally 7 electrons are having in the outermost shell. So, okay, so these halogens readily to gain 1 electron from any other atoms to attain the nearest noble gas configuration. Understood? An oxidizing agent, what do you mean by oxidizing agent? An oxidizing agent is one which is ready to gain an electron. Oxidizing agent means it is ready to gain 1 electron and it oxidizes other elements. Okay, it oxidizes the other elements by gaining electrons. By gaining electron, that is called oxidizing agent. Okay, so halogens, all the halogens has the NH2 and P5 configuration. So each halogen is ready to get the 1 electron to get the stable configuration. So all the halogens act as the oxidizing agent. So all the halogens act as the oxidizing agent. This is the question number 37. And then question number 38, mention any 2 anomalous properties of second period element. Mention any 2 anomalous properties of second period element. The page number 89. Page number 89. Here. The last paragraph from 3rd line onwards have to mark. Last paragraph from 3rd line onwards. Lithium and beryllium form more covalent compounds unlike the alkali and alkali earth metals which predominantly form ionic compounds. Okay. Lithium, beryllium, second group elements to form covalent compounds. Okay. So, but all the other except lithium and beryllium, all the other alkali and alkali earth metals. Alkali metal means first group elements. Alkaline earth metals means second group elements. So lithium is first group, beryllium is second group. Okay, so this lithium and beryllium form more covalent compounds, unlike the alkali and alkali earth metals which predominantly form ionic compounds. Okay, the elements of the second period. Now we are studying anomalous properties of second period element. The elements of the second period have only 4 orbitals in the valence shell. Second period elements. This is the second period element, page number 74 in your period in your textbook having the periodic table. So this is the second period element. So all the second period elements have 2s and 2p orbitals. Okay, 2s and 2p orbitals. For example, sodium, magnesium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So all the second period elements has the 2s and 2p orbital only for the outermost orbit. Okay, in the valence shell, and have the maximum covalence of 4. Okay, so because of only 2s and 2p orbital having the outermost orbit. Okay, you know this. 2s, one s orbital and 3p orbital. Okay, 2px, 2py and 2pz. Okay, totally how much orbitals are having here? Totally 4. 1, 2, 3, 4. So maximum covalence. What do you mean by covalence? Covalence means total number of orbitals available in the valence shell. That is called covalence. Okay, total number of orbitals available in the valence shell. So that is called the covalence. So second period element, all the elements of the 2s2 and 2p, 2s and 2p orbital, 2s and 2p orbital only having. Okay, so the maximum covalence 4. 4 electrons only we can add here. Understood. So, but whereas the other members of the subsequent period, so other members of the subsequent, the other period elements have more orbitals. Okay, other period elements have more orbitals. Okay, so in their valence shell and shows higher valences. So, other members of the subsequent period has the more number of more orbitals in their valence shell and shows higher valences. For example, boron forms boron tetrafluoride and aluminium forms aluminium hexafluoride. Okay, boron forms boron because boron, the outermost shell having only 2s and 2p orbital. Maximum covalence is 4. Okay, but the aluminium can form aluminium hexafluoride 3 minus. Okay, so boron can form only boron tetrafluoride only. Maximum covalence 4. But all other elements can form more number of compounds. Okay, so aluminium can form aluminium hexafluoride. Understood? These are about the anomalous properties of the second period elements. Okay, understood? And next question. Question number 39. Explain the Pauling method for the determination of ionic radius. Explain the Pauling method for the determination of ionic radius. Page number 83. Page number 83. This is the ionic radius. So ionic radius of a metal we can determine by the Pauling scale. Okay. So ionic radius of the univalent crystal can be calculated using Pauling method. Pauling's method from the inter-ionic distance, the distance between the nuclei of the cation and the anion. Okay. In Pauling method we can use to calculate the ionic radius of the univalent crystal. Univalent means only one valent element crystal. Okay, one valent crystal. That means the valence electron only one. Valence of that elements is only one. Okay, so ionic radius of univalent crystal can be calculated using Pauling's method from the inter-ionic distance between the nuclei of the cation and the anion. Okay, so for example, sodium fluoride. Okay, so we can calculate we can calculate by the Pauling scale for the by the internuclear distance between the two this is cation and the anion. So Pauling assumed that ions present in a crystal lattice are perfect sphere, and they are in contact with each other. Therefore, the D is equal to RC plus or A minus. Okay, so D means interionic distance. That is RCA plus or A minus. Okay, C plus means cationic distance, and A minus means anionic distance. Okay. And Pauling also assumed that the radius of the ion having noble gas electronic configuration, so sodium plus. Okay, so the Pauling he assumed that the radius of the ion having noble gas electronic configuration. You know sodium atomic number 11. So electronic configuration 1s2, 2s2, 2p6, 3s1. Okay, so when lost this one electron, it becomes Na plus. This is the noble gas configuration. Okay, so Pauling also assumed that the radius of the ion having noble gas electronic configuration, that is Na plus, having 1s2, 2s2, 2p6 configuration, is inversely proportional to the effective nuclear charge felt at the periphery of the ion. Effective nuclear charge. Okay, so Pauling, he proposed the ionic radius by the interionic distance. Okay, so he assumed the interionic distance. Okay, so it is inversely proportional to, this ionic distance is inversely proportional to the nuclear charge felt at the periphery of the ion. Okay, so here that is RCa plus, it is inversely proportional to the effective nuclear charge of the cation. Okay, like that radius of the anion, it is inversely proportional to the effective nuclear charge of the anion. Okay, where ZFF is the effective nuclear charge. So effective nuclear charge, how can we calculate the effective nuclear charge? Effective nuclear charge is calculated, it is equal to Z minus S. Already we studied Z means atomic number, S means screening constant. Dividing the equation 2 by 3. Dividing the equation 2 by 3. So we get RC plus by RA minus is equal to Z EFF A minus. This is the inversely proportional. So when we are dividing, it becomes numerator. Okay, so Z EFF A minus by Z EFF C plus. On solving the equation 1 and 2, this equation 1, this is the equation 1 and 4. Okay, on solving this equation 1 and 4, we get the values of RC plus and RA minus can be obtained. We get the interionic distance of RC plus and RA minus. Okay, understood? And next question. Explain the periodic trend of ionization potential. Explain the periodic trend of ionization potential. Page number 84 and 85. Page number 84 and 85. So periodic trends of the ionization of ionization energy. Here the periodic trends in ionization energy along the periods and along the group. Okay, so here this is the ionization energy. Here to here you have to mark periodic trends in ionization energy. Ionization energy, you know, it actually increases along the period with few exceptions. Okay, as discussed earlier, when we move from left to right along the period, the valence electron are added to the same cell. As at the same time protons are added to the nucleus. This successive increase if nuclear charge increases the electrostatic attractive force on the valence electron, and more energy is required to remove the valence electron, resulting in high ionization. You know, okay, you know, already we studied about that. When we are moving from left to right, the atomic size is decreased because when we are moving from left to right in the periodic table, the atomic number increases. Okay, atomic number increases. Okay, atomic number increases. When your atomic number increases, the atomic nuclear charge also increases. Okay, so increase the nuclear charge, the attractive force is increased. Attractive force between the nucleus and the outermost electron is increased. Okay, so due to the attractive force, the size of the atom will be very decreased. Okay, so ionic radius will be ionization energy. Atomic size decrease. So when we are removing the electron from the outermost orbit, we should give the high ionization energy. High energy, that is called ionization energy. So ionization energy will be high. Okay, understood? And periodic variation, the periodic trends in ionization energy along the groups. Okay, along the groups, here to here you have to mark. The ionization energy decreases down a group. Ionization energy decreases down a group. Ionization energy decreases. Okay, already we studied about that. As we move from down a group, the valence electron occupies new shell. Valence electron. Okay, so when we are moving from left to right, atomic number increases, the valence electron added to the same cell. Number of cell not increased. Okay, only electron and proton only increase. Okay, but along the group, okay, when we are moving top to bottom, the atomic number increases, also the number of shells also increases. So new electron, the valence electron occupy the new shell. Okay, so the distance between the nucleus and the valence electron increases. The distances increase. Okay, so the nuclear force of attraction on the valence electron decrease. Okay, nuclear force is decreased there. Easily we can remove the electron. Okay, so hence the ionization energy decrease down the group. And this is the question number 40. And question number 41. Explain the diagonal relationship. Explain the diagonal relationship. Page number 90. Page number 90, diagonal relationship. On moving diagonally across the periodic table. Diagonally means this like. Okay, the first member of the first group and the second member of the second group. Okay, this is the diagonal. On moving diagonally across the periodic table, the second and third elements show certain similarity. The second and third elements show certain similarity, even though the similarity is not same as we see in a group. Okay, so similarity it is not same we see in the group. Okay, understood. So for example, lithium, sodium, this is the group, beryllium, magnesium, boron, aluminium, and carbon, silicon. Okay, here the diagonal relationship with the lithium and magnesium, the character will be same. And beryllium and aluminium, the chemical properties is same. And the boron and the silicon, the properties will be same. Understood? Some property similar. The similarity in properties existing between the diagonally placed elements is called diagonal relationship. So what do you mean by diagonal relationship? The similarity in properties existing between the diagonally placed elements is called diagonal relationship. Okay, I have to mark. And question number 42. Why the first ionization enthalpy of sodium is lower than that of magnesium, while the second ionization enthalpy is higher than that of the magnesium. Okay, question number 42. So here this is the electronic configuration of sodium. Sodium, that is neon 3s1. Okay, neon means sodium electronic configuration, atomic number 11. So electronic configuration 1s2, 2s2, 2p6 and 3s2. Here neon, one of the noble gas, nearest to noble gas here neon. So neon atomic number 10. So for this 10 electron we can take as the neon. Okay, noble gas, and 3s1. 3s not 3s to 3s1. Okay, so neon 3s1. But magnesium atomic number 12. So here neon 3s2. So sodium has one valence electron 3s1, and by losing this electron it attains stable configuration. When it lost this one electron, sodium it lost this one electron, it get the stable configuration, neon configuration it get. Therefore the first ionization of sodium is less than magnesium. The first ionization energy. Okay, so sodium it lost one electron, it becomes Na plus. So one electron loss. The energy, there is the first ionization energy. This first ionization energy will be very low when compared to magnesium. Magnesium, when we are removing the first electron, it is difficult because 2 electrons are having here. More energy we should give. We should give more energy to remove the electron. Okay, so this is the first ionization energy of sodium, it is low because sodium only one electron, so we can easily remove. Okay, so sodium ionization energy First ionization energy very low when compared to magnesium. Okay, after removing an electron, the sodium at a noble gas configuration, whereas magnesium has one electron left. Magnesium also one electron left. To remove an electron from sodium, high energy is required. To remove an electron from sodium plus. This is the first ionization energy. When we are giving before ionization energy, first ionization energy, sodium, it give electron and it become Na plus. And after this is now stable. So Na plus, it is stable. Now if we are removing the another one electron from the Na plus ion, it is ionization energy will be high. Understood? So therefore the second ionization enthalpy of sodium is higher than that of the magnesium. But magnesium second ionization energy low because only 2 electrons are having the outermost orbit. So it is easy to remove this 2 electron. Okay, so first 1 electron removed, after only 1 electron having, only 1 electron. So it is easy, we can remove the 1 electron from the magnesium. Okay, but sodium Na plus means it is stable now. Okay, but magnesium, after removing 1 electron, it have the Ne3S1. So only 1 electron. So it can easily remove when compared to Na plus. Mg2 plus, we can remove 1 electron from the Mg plus ions easily, but we cannot easily remove the 1 electron from Na plus ion. Understood? Because Na plus now stable. This is the answer. And question number 43. By using Pauling's method, calculate the ionic radii of K plus and Cl minus ions in the potassium chloride crystal. Given that dk plus and Cl minus is equal to 3.14 Armstrong. This is the distance between. Here one of the crystallite is given. By using Pauling's method, calculate the ionic radii of K plus and Cl minus ion. So distance, internuclear distance given. Internuclear distance is given. Internuclear distance between the K plus ion and the Cl minus ion is given 3.14 Armstrong. Okay, so we have to calculate the ionic radii of K plus and Cl minus ion. Okay, here we know, so one of the formula that is Rk plus plus Rcl minus is equal to, that is internuclear distance between the potassium and chlorine. Okay, so that is Dr plus and DCl minus, that is the 3.14 Armstrong. Okay, otherwise we can write Rk plus plus Rcl minus is equal to 3.14 Armstrong. Okay, the distance between these two nuclei that is given. Okay, so here we have to calculate the ionic radii. Okay, for the Rk plus, this separate ionic radii. Internuclear distance given, we have to calculate the separate ionic radii for the Rk plus and Rcl minus ions. Okay, for that we can use this formula. Now only we studied about that, Pauling's method. Okay, this formula. So Rc plus by Ra minus is equal to Zeff A minus by Zeff of C plus. Okay, C plus and A minus, you know, C plus means cation, A minus means anion. Here R, okay, and here, and Zeff and Zeff of C plus, it is the effective nuclear charge for the anion and cation. Okay, so here effective nuclear charge, we should calculate the effective nuclear charge first. We have to calculate the effective nuclear charge for the cation and anion. So here cation means K plus, anion means Cl minus. Okay, so potassium chloride KCl, when we are dissociation of this ion, potassium chloride crystal, K plus and Cl minus ions are having. Okay, so this first we should calculate the effective nuclear charge for the K plus. K plus is equal to Z minus S. What is the formula for calculate the effective nuclear charge? Z minus S. Z here, Z is the atomic number, S means screening constant. Okay, So here atomic number for the potassium is 19, we know. Electronic configuration 1s2 2s2 2p6 3s2 3p6 4s1 because atomic number 19. Okay, so but here we have to calculate the effective nuclear charge for the K plus. K plus means 1 electron lost. Okay, so K plus is good electronic configuration 1s2 2s2 2p6 3s2 3p6. The 4s 1 electron lost. It lost. Okay. So, for calculate the effective nuclear charge, we know the screening constant. Okay, we should know the screening constant. We should calculate the screening constant. Here is equal to 19. 19 is the atomic number, Z. So, formula is Z minus S. So, Z means 19 minus S. We have to calculate the S value. How we can calculate the S value? That is given in your textbook. How can you calculate the effective nuclear the screening constant? Yes means this is the formula. Okay, this is the one of the table column, 2 table column given the values. Okay, so we should separate the shells. Okay, this is the last orbit. NS3s2 3p6 lost orbit. So we can take this is the N shell. Okay, N shell. And before this last orbit, that is penultimate shell, there is N minus 1 shell. This is N shell. This is N minus 1. 1 before the last orbit. N minus 1 shell. And the remaining 1 is 2. So it is the inner shell. That is also N minus 2 shell. Okay. So here value for N shell, what is the value for N shell? 0.35. Okay. So N last orbit, N value 0.35. Understood? So here 0.35 into outermost electron. Here how much electrons are having? Totally 6 plus 2, 8 electrons are having. So but we can less 1 electron. When we are taking the last outermost orbit, 1 electron less we should take. 1 electron less we should take. This is the screening constant. This is the rules for the Slater's rule. Already we studied about this is the Slater's rule. Okay, so when we are considering the N shell, we should minus the total minus 1 electron from the total number of electrons. So N shell totally 8 electrons are having. We should minus 1 electron from the last orbit. Okay, so 8 minus 1, 7 plus. And then next shell N minus 1 shell. N minus 1 shell, what is the value? N minus 1, 0.85 into how much electrons are having? 8 electrons. Okay, 0.85 into 8 plus last orbit N minus 2 and others 1. Only 1 value 1 into how much electron? 2 electrons. So it's equal to 19 minus, when we are multiplying this and this 2 and this 2, this one, so we get finally multiplication and adding, finally we get 11.25. Okay, 11.25. So when subtracting 19 minus 11.25, we get 7.75. Okay, this is the effective nuclear charge for the K plus. And effective nuclear charge for the Cl minus N is equal to Z minus S. Here is Z, atomic number for chlorine 17. And S means the screening constant. If we are calculating the screening constant, we should write the electronic configuration. So 17 means electronic configuration 1s2 2s2 2p6 3s2 3p5. Okay, 3s2 3p5 for chlorine. But here we are taking Cl minus. Cl minus means 1 electron extra having here. 1 electron extra having. So what is the valence outermost configuration? 3s2 3p6. stable configuration. Okay, understood. So this last orbit we can take as the n shell before the last orbit, that is penultimate shell, we have to take as the n minus 1 shell. The before the inner shell we are taking n minus 2 shell. So how we can calculate the effective nuclear charge is that ff of Cl minus is equal to 17 minus what is the value for the n minus 1 last n minus n shell means n last orbit value 0.35. Okay, 0.35. How much number of electrons are having here? Totally 8. So when we are taking last orbit, we should less 1 electron from the total number of electrons. Totally 8 electrons. So 8 minus 1 is equal to 7. Plus n minus 1 shell, what is the value? 0.85 into how much electron? 8 electron. Plus last inner shell, n minus 2 shell, what is the value? 1. So 1 into how much electron? 2. So we get 17 minus 11.25. Same value we get. So when we are subtracting 17 minus 11.25, we get 5.75. So RK plus by RCl minus is equal to, what is the formula? RK plus by RCl minus is equal to ZEFF Cl minus by ZEFF K plus. So what is the value for the ZEFF Cl minus value? 5.75 and K plus value 7.75. By dividing these two values we get 0.74. So here RK plus by RCl minus is equal to 0.74. Okay, so from this we have to calculate, we are going to calculate the RCl minus value first. Okay, so here for that the RK plus first we can take on here. RK plus is equal to cross multiplication. When you are crossing the multiplication, so we get RCl plus RK plus is equal to 0.74 into RCl minus. Okay, this is the equation number 2. Substitute the RK plus this value what? 0.74 RCl minus. RK plus value is 0.74 into RCl minus. Substitute the value, the RK plus value in equation 1. What is the equation 1? This is the equation 1. RK plus RCl minus is equal to 3.14 Armstrong. So this equation, from to this equation we have to substitute the value of RK plus. This is the RK plus value. What is the RK plus value? 0.74 RCl minus. 0.74 RCl minus plus RCl minus is equal to 3.14 Armstrong. Here when we are adding these two, 0.74 into RCl minus plus RCl minus means 1 RCl. Okay, 1 RCl means 0.74 plus 1 means 1.74 RCl minus. 1.74 RCl minus. Understood? So it's equal to 3.14 Armstrong. So when we can get out the RCl minus. So RCl minus is equal to 3.14 by 1.74. So we get RCl minus is equal to 1.81 Armstrong. This is the radius of the anion. From the radius of the anion value, we can calculate the radius of the cation. So this is the equation number 1. RK plus RCl minus is equal to 3.14 Armstrong. So the K plus value, we have to calculate the RK plus value. RCl minus value we know 1.81 Armstrong. So we have to calculate the RK plus value. RK plus value. Okay, so RK plus is equal to RCl 3.14 minus RCl. Okay, RK plus is equal to 3.14 minus RCl minus. Okay, so what is the value? 3.14 minus RCl value 1.81. We get, when subtracting these two, we get the 1.33 Armstrong. Understood? These are about the 43 question. And what is the 44? Question number 44. Explain the following, given appropriate reason. Explain the following, give the appropriate reason. First Question. Ionization potential of nitrogen is greater than that of oxygen. Ionization potential of nitrogen is greater than that of oxygen. A reason. What is the reason? Okay. The answer. Electronic configuration of nitrogen. We have to compare the nitrogen and oxygen. What is the ionization potential? Here, electronic configuration of nitrogen is 7. So, the atomic number 7, electronic configuration 1s2 2s2 2p3. This is the orbital diagram. Okay. Like that, electronic configuration of oxygen, atomic number 8. So, electronic configuration 1s2 2s2 2p4. So, this is the orbital diagram. We know the nitrogen has a half-filled configuration. Nitrogen has a half-filled. Half-filled means this half-filled configuration, which is much more stable than an incomplete p orbital of oxygen. This is incomplete orbital. This is not half-filled or not completely filled. Okay. So this is the half-filled. We know half-filled or completely filled orbital only stable. So here nitrogen is stable now when comparing oxygen. Understood? So oxygen, which would need to give up one of each electron to attain the stability of nitrogen. One electron, when the oxygen atom, it need to give one electron to get the stability of nitrogen atom. Okay, hence nitrogen would require more ionization energy because it is stable. Okay, the nitrogen is half-filled configuration, so it is stable. So if we want to remove the one electron from the outermost orbit, we should give more energy because it is stable. But oxygen, we can easily remove this electron. Okay, so the ionization energy is greater ionization energy has nitrogen than the oxygen atom. This is the first question. What is the second question? First ionization potential of carbon atom is greater than that of boron atom, whereas the reverse is true is for the second ionization potential. Here comparison comparison between carbon and boron atom. The first ionization potential of carbon is greater than the boron atom, whereas the second ionization potential, it is reverse. Reverse is true. Reverse is true means boron is greater than carbon. Okay, what is the reason? So electronic configuration of carbon, you know electronic configuration, atomic number 6, so electronic configuration 1s2 2s2 2p2. This is the orbital diagram. Like that, electronic configuration of boron is atomic number 5, 1s2 2s2 2p1. This is the orbital diagram. 1s2, s orbital 2 electron, 2s orbital 2 electron, 2p, x only 1. The size of the carbon atom is smaller than boron. Here the size of the carbon, it is smaller than the boron. Okay, boron, because boron atomic number 5, but carbon atomic number 6. But these two atoms having the same subshell, okay, same orbitals. Okay, so due to the higher atomic number, size will be low for the carbon atom than boron. So the valence electron of carbon has greater nuclear charge than that of boron. The valence electron of carbon atom, it is greater nuclear charge because number of electron increase, also number of proton also increase. Nuclear charge is increase for the carbon atom. So greater nuclear charge are having. Hence the first ionization energy of carbon is greater than that of the boron. Okay, so due to the higher nuclear charge, we cannot easily remove the one electron. Okay, so if we want to remove the one electron from the outermost orbit, we should give more energy. Okay, understood? Then boron. Boron, because only one electron having, we can easily remove. Okay, so however, the second ionization energy of boron is higher than that of the carbon. Okay, here this the second ionization energy means when the first energy carbon, when losing the one electron, we get a carbon, get the carbon plus. Here the outermost electron 1s2 2s2 2p1 2p1 one electron get lost. Okay, but in the case of boron when it lost only one electron having the outermost orbit 2px orbit, so when it lost this one electron easily. Okay, this the first energy. So first energy of carbon atom only high when compared to boron. Okay, energy higher, energy first energy higher for the carbon atom than boron, because boron only one electron, we can easily remove the one electron. So ionization energy will be low than the carbon atom. But the second ionization energy, okay, so first ionization carbon to become carbon plus, boron to become boron plus. So here only the carbon atom having 1s2 orbital 2 electron, 2s orbital 2 electron, and 2px electron only 2px. But boron atom 1s2 orbital and boron plus 1s2 2s2 orbital only, 2p orbital not. So for the boron atom it is completely filled when compared to carbon only one electron having. So carbon the second energy when comparing boron atom, carbon is very low second addition, because only one electron having, we can easily remove the one electron, okay, to get the stable configuration. But boron, it is now stable. If we want to remove one electron, we should give more energy. Understood? So this because after losing one electron, boron has a fully filled orbital 2s2 than the carbon 2p1. So fully filled orbitals have more stability than the partially filled orbital. So greater amount of energy will be needed to remove the electron from the boron. So in this case, the second energy of boron is higher than that of the carbon. And this is the second question. What is the third question? The electron affinity. The electron affinity values of beryllium, magnesium and noble gases are 0, and those of nitrogen 0.02 eV and phosphorus 0.80 eV are very low. Okay, so what is the question? Our question, electron affinity value. Electron affinity. The beryllium, magnesium and noble gas, it is 0. Okay, and those of nitrogen and phosphorus very low. What is the reason? So electron affinity of beryllium and magnesium and noble gases are almost 0, because both beryllium having the completely filled configuration, the magnesium also having the completely filled. Okay, so 1s2 2s2. 2s2 means 2 s orbital 2 electron. Magnesium also 1s2 2s2 2p6 3s2. Okay, having s orbital fully filled. For the two atoms, s orbital fully filled. Okay, in their valence shell. Fully filled orbitals are more stable due to symmetry. So these two orbitals are stable because it is in symmetry now. Therefore, these elements would be having least tendency to accept electron. This beryllium and magnesium, it is least tendency to accept electron. Hence, beryllium and magnesium would be having 0 electron affinity. Okay, 0 electron affinity. But in the case of nitrogen, atomic number 7, electronic configuration 1s2 2s2 2px1 2py1 2pz1. Phosphorus 15 atomic number, so 1s2 2s2 2p6 3s2 3p3. Here also half-filled configuration. So nitrogen and phosphorus having half-filled configuration. So half-filled subshell are most stable due to symmetry. Thus nitrogen and phosphorus having least tendency to accept electron. Hence have low electron affinity. Electron affinity means what do you mean by electron affinity? Electron affinity means amount of energy released. When we are adding electron in the outermost orbit. Okay. So here the for the beryllium and magnesium, completely filled electron, completely filled. So this is the beryllium electronic configuration 1s2 2s2, completely filled. Magnesium also completely filled s orbital. So we cannot easily remove. We no need to add the electron here. No need to add the electron for the beryllium atom. No need means no space to add the electron. So electron affinity will be zero electron affinity. But in the case of nitrogen, phosphorus, half filled. So half filled, this completely filled is more stable than half filled. Okay, so half filled orbital, we can it is stable, but some cases we can add the electron. When combining other elements, we can add the electrons in the half filled orbit. So, but it is the very least electron affinity, only small electron affinity. Okay, because it is stable. Understood. This is the third question. What is the fourth question? Fourth question, the formation of fluoride F minus gas from F gas is exothermic, while that of O2 minus gas from O gas is endothermic. What do you mean by exothermic and what do you mean by endothermic? Exothermic means heat is liberation. Endothermic means heat is absorption. Exo means energy is released. Endo means energy absorbed. Okay. Here, the fluorine is highly electronegative in nature. Fluorine is highly electronegative. So, it always attracts the electrons and also it has the 6 electron in the valence shell. So, therefore, it gains the electron, its octet become stable and releases the energy. Okay, therefore, as it gain the electron, its octet becomes stable. Okay, so it always attract their own electron and release the energy. Okay, that is so exothermic. So that is, we know about the electron affinity means when we are adding the electron from the in the outermost shell, it release the energy. Okay, so when fluorine atom, when it always attracts the electron easily. Okay, so when one electron it is added to the fluoride Fl minus fluorine atom, it becomes F minus ion, fluoride ion. Here this reaction is exothermic. Okay, exothermic. While in oxygen, the addition of first electron is exothermic. First electron easily we can add. But this, when we are adding the second electron means the oxygen second electron we are not when we are adding, the greater repulsive force experienced there. Okay, so but addition of second electron experiences high repulsive force, so needs extra external energy to enter outer shell, hence endothermic in nature. Okay, we know exothermic means it is energy releasing of energy, that is exothermic. Endothermic means absorbing energy absorbing. Okay, so the fluorine it is one of the more electronegative, so it is easily attracts the electron. More electron negative it is easily attracts the electron. So it releases the energy. When adding one electron, it releases the energy. But in the case of oxygen, one electron we can easily add. Okay, when we are adding one electron in the outermost orbital of oxygen, it releases the energy. So it is exothermic. But another one electron, second electron, we are adding second electron in the outer shell of the oxygen atom, the repulsive force there experience. Okay, repulsive force because only one electron we are adding and another one electron when we are going to add, their greater repulsive force acting there. Okay, so because of the greater repulsive force, we can give the extra energy, to add this one electron. So the reaction is endothermic. Okay, that is an endothermic in nature. This is about the 44th question. And what about the 45 question number 45? What is screening effect? Page number 80. Screening effect, page number 80. The screening effect means the repulsive force between the inertial electron. Okay, the third paragraph, effective nuclear charge, the paragraph, third paragraph, fourth line onwards. Third paragraph, fourth line onwards. Okay, so what is screening effect? So here, the repulsive force between the inertial electrons and the valence electrons leads to a decrease in the electrostatic attractive forces acting on the valence electron by the nucleus. Okay, repulsive force between the inertial electron and the valence electron leads to a decrease in the electrostatic attractive force acting on the valence electron by the nucleus. Thus, the inertial electrons act as a shield. Inertial electron act as a shield between the nucleus and the valence electron. Okay, one of the shield takes place between nucleus and another shell electrons. That is called the screening effect. Okay, and next question. Question number 46. Briefly give the basis for Pauling scale electronegativity. Briefly give the basis for Pauling scale electronegativity. Page number 87. Here, the Pauling scale electronegativity means the Pauling, he assigned arbitrary value of electronegativities for hydrogen and fluorine as 2.1 and 4.0 respectively. Okay, he assigned one of the arbitrary value. Arbitrary means it is not the approximately value for the electronegativity for the hydrogen and fluorine. Hydrogen 2.1 and fluorine 4.0. Okay, so based on this electronegativity values for the other elements can be calculated using the following expression. Using these two values, we can calculate the electronegativities of other elements using this expression. One of the expression he given, there is chi A minus chi B is equal to 0.182 root of E of A minus B, E of AB minus E of AA into E of BB. Okay, and half, the power having half, where EAA and EBB are the bond dissociation energies of AB, A2 and B2 molecules respectively. Okay, bond dissociation energy for the A and B molecule and AA means A2, okay, and BB molecule, BB means B2. Okay, there is same kind of molecules, this same kind of molecule A2, B2 same kind of molecule, AB means two different kinds of molecule. So that is the dissociation energy. The electronegativity of any given element is not a constant, and its value depends on the element to which it is covalently bound. The electronegativity of any given element is not constant. Okay, the value will be differ. It is based on the element which is covalently bound. The electronegativity values plays an important role in predicting the nature of the bond. Because of this, we can identify which the bond. Okay, based on the electronegativity value, we can identify whether it is ionic bond or whether it is covalent bond. We can identify nature of bonding. And here, what about the last question? Question number 47. State the trends in the variation of electronegativity in group and periods. Electronegativity variation along the period and along the groups. Okay, so variation of electronegativity in period. The electronegativity generally increases across the period from left to right. Electronegativity increase, okay, because of the greater attractive force having between the nucleus and the outermost electron. As discussed earlier, the atomic radius decreases in a period as the attraction between the valence electron and the nucleus increases. Hence, the tendency to attract the shared pair of electrons increases. What do you mean by electronegativity? Means tendency of an element present in a covalently bonded molecule. Okay, tendency of an element, when an element is present in covalently bonded molecule, it has the tendency to attract the shared pair of electron towards itself. Okay, so when we are moving left to right, the atomic size decreases. So the nuclear charge also increases. Nuclear charge increases. So the greater attractive force having between the nucleus and outer electrons. So it can easily attract the shared pair of electron towards itself. Okay, so this is the one of the graph, variation of electronegativity along the period. So this is the atomic number. This is the for second period elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. Okay, so here electronegativity increase along the periods. Okay, so and along the group means variation electronegativity in a group, the electronegativity generally decreases down the group. Okay, so when we are moving down the group, electronegativity decrease. Okay, as we move from down the group, the atomic radius increases and the nuclear attractive force on the valence electron decrease. Okay, so when we are moving down the group, atomic number increases, but atomic size will be increased. Why? The extra electron is added to the new shell. Number of shell increases. When you are moving down the group, number of shell increases. So the attractive force will be decreased there between the nucleus and outer shell. So because the distance is increased. But when we are moving left to right, the distance will be decreased because the atomic size decrease. Because the increase in number of electron is added the same shell, extra shell not having. Same shell electrons are added. So the nuclear charge also increase. Okay, so greater nuclear charge, the attraction of nucleus and the outer shell is electron is increased. But when we are moving down the group, the distance between the nucleus and outer shell is increases. So the attractive force here decrease. Okay, because of the decreasing attractive force, electronegativity will be decreased. Understood? So this is the up to here you mark, and this graph also you have to draw. This is the variation of electronegativity along the first group. This is the first group element: lithium, sodium, potassium, Kr, no, potassium, rubidium, cesium. Okay, so it gradually decrease. That's all about the book back question for the third unit. Okay, everyone should study the book back question, and the book in question also you should read. Okay, so today assignment first upon we should complete the fourth unit. After that we will come to the second unit, third unit. Okay, to study. So here the today's assignment, question number 24, and question number 27. Okay, page number 122, question number 24 and question number 27. Two questions you should study and write assignment. Okay, you can you should study extra question also. If you have time, you should study other questions. Okay, students. Thank you, students. Thank you.